In a previous lecture, I introduced the Riemann curvature tensor, R mu nu alpha beta, by considering a vector parallel transported around a loop. So here's the vector u, and here's the loop. And the result is that the change in the vector is equal to R mu nu alpha beta, the vector u, and then a factor of A, which describes the loop. A is an antisymmetric tensor. In carrying out this calculation, we found that the Riemann tensor can be defined in terms of the Christoffel symbols as partial alpha gamma mu beta nu minus partial beta gamma mu alpha nu plus gamma mu alpha sigma gamma sigma beta nu minus gamma mu beta sigma gamma sigma alpha nu. So this is the Riemann tensor, or the components of the Riemann tensor, and it completely characterizes the intrinsic geometry of space-time. So the Riemann tensor, written this way, is a type 1,3 tensor, which means it has 4 indices, and each of those indices can take on any of the values 0, 1, 2, or 3 in 4-dimensional space-time. So that means there are 4 times 4 times 4 times 4 components. That's 256 components. So that's a lot of components, but fortunately they're not all independent. We can see that these components are not all independent by examining the symmetries of the Riemann tensor. So one symmetry that we already know from the way that Riemann was constructed is that it's antisymmetric under interchange of the last 2 indices alpha and beta. So if we write down R mu nu beta alpha, we swap alpha and beta. Notice that these 2 terms just switch roles. So this term becomes this term and this term becomes this term, but there's an extra minus sign. And likewise, these 2 terms just swap places when we switch alpha and beta, but there's an extra minus sign here. So R mu nu beta alpha is equal to minus R mu nu alpha beta. And that means for each value of mu and nu, we can view this as an antisymmetric matrix. So instead of 16, 4 times 4 is 16 independent components, there are only 6 independent components for each value of mu and nu. So this is one symmetry of Riemann which reduces the number of independent components. There are other symmetries of the Riemann tensor, but they're a bit harder to recognize by just examining this expression. So what I'm going to do is use a trick. It's a very powerful trick, and that is to examine the Riemann tensor using locally Minkowski coordinates. Or sometimes they're called Riemann normal coordinates. So the idea of Riemann normal coordinates, and let me abbreviate Riemann normal coordinates as RNC. The idea is that in a neighborhood of any point P, we can always choose coordinates such that the metric at point P looks just like the flat space-time metric in Minkowski coordinates, so that's -1, 1, 1, 1 down the diagonals. And also, the coordinates can be chosen such that the derivatives of the metric at that point vanish. And of course, that is equivalent to saying that the Christoffel symbols at point P vanish. So how do we know that these Riemann normal coordinates exist? How do we know that it's possible to find a coordinate system where the metric looks like eta mu nu, and the derivatives of the metric vanish at a point. Well, if you'll recall, in an earlier lecture I derived Fermi normal coordinates, which are coordinates that have these properties. G mu nu is eta mu nu, and the derivatives of G mu nu vanish, all along a geodesic. So all we need to do is find a geodesic through this point, and then construct Fermi normal coordinates. So this is a geodesic. And Fermi normal coordinates is a set of coordinates that have these properties all along the world line, and in particular they'll have these properties at point P on the world line. Now let's evaluate the Riemann tensor at point P using Riemann normal coordinates. If we recall the definition of the Riemann tensor, it looks like this. And because the Christoffel symbols vanish at point P, both of these terms are equal to 0. Now the vanishing of the Christoffel symbols at point P does not imply that the derivatives of the Christoffel symbols vanish at point P. So in this case, the Riemann tensor looks like R mu nu alpha beta evaluated at point P in Riemann normal coordinates. This is partial alpha gamma mu beta nu minus partial beta gamma mu alpha nu. And this term, of course, is just the same as this term, but with alpha and beta reversed. So let me write this second term as indicating that it's the same as the first term, but just with alpha interchanged with beta. And now we can put in the definition of the Christoffel symbols. So this is partial alpha of 1/2 G mu sigma, partial beta G nu sigma minus, or rather plus, partial nu G beta sigma minus partial sigma G beta nu. And then we have this term where alpha and beta are switched. Now this derivative operator, partial alpha, acts on everything in the square brackets, of course. In particular, when it acts on the inverse metric, what we have is, well, this can be written as minus G mu lambda partial alpha G lambda gamma G gamma sigma. But evaluated at point P, this is, of course, 0. So in effect, we can just let this derivative operator pass right through this inverse metric. Write this as 1/2 G mu sigma times partial alpha partial beta G nu sigma plus partial alpha partial nu G beta sigma minus partial alpha partial sigma G beta nu. And then, of course, we have the terms where alpha and beta are swapped. Keep in mind that we're evaluating this in Riemann normal coordinates where the first derivatives of the metric vanish, but that does not imply that the second derivatives of the metric vanish. On the other hand, look at this term. This has partial alpha partial beta, and of course partial derivatives commute. So when we swap alpha and beta and then put in a minus sign, the term corresponding to this one will cancel this term. So those two terms are gone. And what we're left with for the Riemann tensor in Riemann normal coordinates is 1/2 G mu sigma. This term is partial alpha partial nu G beta sigma. This term is partial alpha partial sigma G beta nu. And then we have minus the terms we get when we switch alpha and beta. So this would be partial beta partial nu G alpha sigma and plus partial beta partial sigma G alpha nu. Now let's lower this index mu. This, of course, becomes delta sigma mu, and contracted with the sigma here just turns these sigmas into mu's. So what we're left with then is R mu nu alpha beta with all lower indices is equal to 1/2 partial alpha partial nu G beta mu minus partial alpha partial mu g beta nu minus partial beta partial nu g alpha mu plus partial beta partial mu g alpha nu. So these are the components of the Riemann tensor written as a 0,4 tensor and in Riemann normal coordinates. Now let's use this result to examine the symmetries of the Riemann tensor. And for the moment, let's pretend that we don't already know that the Riemann tensor is antisymmetric in its last two indices. So examining this expression, we can pretty easily recognize that this is antisymmetric if we exchange alpha and beta. If we swap alpha and beta, then this term and this term just switch roles, but with a minus sign. And similarly, this term and this term just switch places, but with a minus sign. So we would be able to easily deduce from examining this that r mu nu alpha beta is equal to minus r mu nu beta alpha in Riemann normal coordinates. But what does this tell us about the symmetries of the Riemann tensor in an arbitrary coordinate system? Let's let x mu denote the Riemann normal coordinates, and let's use x bar mu to be some arbitrary coordinate system. Then from the tensor transformation rule, we know that the components of the Riemann tensor in the barred coordinates, let's call that r bar, rho, sigma, lambda, gamma, is given by partial x mu with respect to x bar, rho, and so forth. We'll have r mu nu alpha beta here. And let me complete these factors. This is partial x nu with respect to x bar, sigma, partial x alpha with respect to x bar, lambda, partial x beta with respect to x bar, gamma. So this is just the tensor transformation rule between the unbarred and the barred coordinates. And now, because we know that in the unbarred coordinates, the Riemann normal coordinates, the components of the Riemann tensor satisfy this relation, we can write this as equal to the same factor times minus r mu nu beta alpha. But this combination is precisely r bar rho sigma gamma lambda. And then with the minus sign, what we find is that r rho sigma lambda gamma is equal to minus r bar rho sigma gamma lambda. So we can see from this argument that the antisymmetry of the Riemann tensor in its last two indices holds in any coordinate system, and all we needed to do to come to that conclusion is to recognize that it's antisymmetric in its last two indices using Riemann normal coordinates. So we'll use this same type of reasoning to identify other symmetries of the Riemann tensor. We'll identify them as symmetries using Riemann normal coordinates, and then we'll know from using this type of argument that the symmetry must hold in an arbitrary coordinate system. So here I've rewritten the expression for the Riemann tensor in Riemann normal coordinates, and we can use this to look for other symmetries. One symmetry that's not hard to spot is if I interchange the first two indices, it's antisymmetric. So notice that here we have nu mu, here we have mu nu. So swapping nu and mu just exchanges these two terms but with a minus sign, and likewise here swapping mu and nu just reverses these two terms and we have an overall minus sign. So from here we conclude that r mu nu alpha beta is equal to minus r nu mu alpha beta in Riemann normal coordinates, but now because we know this is a tensor relation, we can argue that this holds in any coordinate system. Another symmetry of the Riemann tensor can be found in the following way. Here I've repeated the expression for the Riemann tensor in Riemann normal coordinates, and now let's write down r alpha beta mu nu. In other words, let's just swap these indices. Mu becomes alpha, nu becomes beta, alpha becomes mu, and beta becomes nu. then this is 1/2 partial mu partial beta g nu alpha minus partial mu partial alpha g nu beta minus partial nu partial beta g mu alpha, and finally we have partial nu partial alpha g mu beta. All right, so now you'll notice this term is the same as this term. This term is the same as this term. Of course, we have to swap the order of these partial derivatives, but we can do that because partial derivatives commute. Also, the order of these indices doesn't matter because G is symmetric. This term is equivalent to this term, and finally this term is the same as that term. Right? So what we found is that in Riemann normal coordinates, r mu nu alpha beta is equal to r alpha beta mu nu. And of course, by the familiar argument, we can say since this is a tensor relation, it holds in any coordinate system. So Riemann has a symmetry in which the first two indices, the first pair of indices, is swapped with the second pair of indices, and that doesn't change the Riemann tensor. Yet another symmetry of the Riemann tensor is r mu nu alpha beta plus r mu alpha beta nu plus r mu beta nu alpha equals 0. And this is straightforward to prove. Just write each of these out in Riemann normal coordinates and add them, and you'll see that each term cancels. And then argue, since that's a tensor relation, it must hold in all coordinate systems. Notice the pattern here is that the first index stays fixed, and the second, third, and fourth indices are cyclically permuted. So to obtain alpha beta nu from nu alpha beta, we just take nu and move it to the end. And likewise here, we just move alpha to the end to get beta nu alpha. So these are just cyclically permuted in the final three indices. So this symmetry, along with the previous symmetries we found, and let me repeat those here. We have r mu nu alpha beta equals minus r mu nu beta alpha. So antisymmetric under interchange of the final two indices. It's also antisymmetric, so minus sign, if we swap the first two indices. It's also symmetric if we swap the first pair of indices for the second pair of indices. So this would be r alpha beta mu nu. So these symmetries reduce the number of independent components of the Riemann tensor from 256 down to just 20. So the independent components are 20 in 4 dimensions, and in 3 dimensions there are 6 independent components, and in 2 dimensions there's just 1 independent component. So these are all of the symmetries of the Riemann tensor, and they're all algebraic relations between the components of the tensor. Now there's another identity satisfied by the Riemann tensor that's very important, that's of a different character because it involves derivatives of the Riemann tensor, and it's called the Bianchi identity. So for the Bianchi identity, we need to examine covariant derivative del sigma of r mu nu alpha beta. Now this, of course, is just del sigma acting on g mu, let's say, rho, r upper rho nu alpha beta. And we can pull this out of the covariant derivative, since the covariant derivative acting on the metric always vanishes, and write this as G mu rho del sigma acting on R rho nu alpha beta. And now let me go ahead and insert the definition of the Riemann tensor components in terms of Christoffel symbols. This is partial alpha gamma, the upper index is rho, nu beta minus partial beta gamma rho nu alpha plus gamma rho alpha sigma gamma sigma. Well, I shouldn't use sigma here because I'm using sigma here. So let me change that to, I don't know, say lambda. Then we're left with nu beta minus gamma rho beta lambda gamma lambda nu alpha. So what we want to do next is to evaluate this expression in Riemann normal coordinates. So we'll use Riemann normal coordinates, and that will greatly simplify our task of identifying this Bianchi identity. So in Riemann normal coordinates, of course, the covariant derivative involves an ordinary partial derivative and then terms with the Christoffel symbols. But when we evaluate those in Riemann normal coordinates, of course, the Christoffel symbol terms vanish. So this is G mu rho partial sigma. And also notice when this partial derivative acts on these combinations of two gammas, it will act on either one or the other of the factors of gamma, but the other factor of gamma, when evaluated in Riemann normal coordinates, will vanish. So all of these terms we can drop, and now we have, here we're left with partial alpha gamma rho nu beta minus this term, and this term is just obtained by swapping alpha and beta. And now let's insert the definition of the Christoffel symbols here. We have, well, G mu rho times partial sigma partial alpha acting on 1/2, I'll put the 1/2 out here, G rho, say gamma, times partial nu G beta gamma plus partial beta G nu gamma minus partial gamma G nu beta. And then of course we have this term where we swap alpha and beta. So notice we have two derivatives here acting on everything in square brackets. And some of the terms that we get will involve both of these derivatives acting on the inverse metric, but those terms will also have first derivatives of the metric, will be proportional to first derivatives of the metric, which vanish in Riemann normal coordinates. So we can drop those terms. Now some of the terms involve one of these derivatives acting on the inverse metric, the other derivative acting on these terms in parentheses here, and so those terms will involve second derivatives of the metric. But the derivative acting on the inverse metric, remember, is proportional to the derivative acting on the metric itself, and that vanishes in Riemann normal coordinates. So we can ignore those terms. The only terms that are non-zero in this expression are the terms in which both of these derivatives act on these terms in the parentheses here to create third derivatives of the metric. So if we go ahead and make that simplification, we have 1/2. This G rho gamma just essentially pulls out from the derivatives. We have G mu rho, G rho gamma times partial sigma, partial alpha, partial nu, G beta gamma plus partial sigma, partial alpha, partial beta, G nu gamma minus partial sigma, partial alpha, partial gamma, G nu beta. And of course, we also have the terms in which alpha and beta are swapped. Now let's notice that this term involves partial alpha, partial beta, and of course, the partial derivatives commute, so this term cancels the corresponding term in here where we swap alpha and beta. And also notice, of course, this is Kronecker delta mu gamma, so when we sum over this repeated index gamma, it will just replace the gamma with a mu. So what we're left with is, and let me remind you, what we're computing is covariant derivative of r mu nu alpha beta, and we're doing this calculation in Riemann normal coordinates. So this is 1/2 of partial sigma partial alpha partial nu g beta mu, and then this term is partial sigma partial alpha partial gamma g nu beta, and I need to change that gamma to a mu. And then we have the terms that come from swapping alpha and beta. So next, I'm going to write down this result again, but I'm going to change the order of the partial derivatives so that the partial with respect to alpha is the first of the derivatives. And I'm also going to make sure that the beta index here is the second index on G. So this is del sigma r mu nu alpha beta equals, in Riemann normal coordinates, 1/2 of partial alpha acting on partial sigma partial nu g mu beta minus partial alpha acting on partial sigma partial mu g nu beta. And then we also have the terms where we swap alpha and beta, so this will be minus partial beta partial sigma partial nu g mu alpha, and then plus partial beta acting on partial sigma partial mu g nu alpha. The Bianchi identity is obtained from the derivative of the Riemann tensor with the first three indices cyclically permuted, so combinations of those expressions. So let me write this down, cyclically permuting the first three indices. So this is del mu r nu sigma alpha beta, and we'll permute the indices once again. This would be del nu r sigma mu alpha beta. I'm not going to write out these in detail. Let's just notice that this first expression is obtained by replacing sigma with mu, replacing mu with nu, replacing nu with sigma. So if I do that, here we have mu, sigma, and the mu becomes nu. So let me just go through and replace all the mu's with nu's, replace all the sigmas with mu's, and replace all the, what are we left with? Nu with sigma. Nu becomes sigma, sigma, sigma. And then to obtain this final expression, we need to change mu to nu, nu to sigma, sigma to mu. So first of all, mu to sigma. So this would become mu to nu. This becomes nu, 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 nu. Nu becomes sigma. So that's sigma, 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 sigma. And finally, sigma becomes mu. So this is mu, 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 mu. All right, what we're going to do now is add all of these three terms together. When we do that, we should find that all of the terms cancel. So for example, looking at this first term with indices sigma, nu, mu, that cancels this term with sigma, nu, mu. Well, we have nu, sigma, mu, but we can reverse the order of the nu and the sigma. So this term cancels this term. And this term with mu, sigma, nu cancels this term with, again, we have to reverse the order of the mu and the sigma. And this term mu, let's see, that canceled this term. And this term, nu mu sigma, cancels this term. And likewise, we can go through here and we have the same cancellation, sigma nu mu, reversing the order of sigma nu. Mu sigma nu cancels here, and this term cancels this term. So all of these added together give 0. So this is the Bianchi identity. Says del sigma r mu nu alpha beta plus, now cyclically permuting those first three indices, del mu r nu sigma alpha beta plus del nu r sigma mu alpha beta equals 0. And of course, we just showed that was true in Riemann normal coordinates, but because this is a tensor relation, we can show that it holds in any coordinate system. Now let's turn our attention to the various tensors that can be constructed from the Riemann tensor. And whereas the Riemann tensor itself characterizes completely the intrinsic geometry of space-time, these other tensors capture different aspects of the curvature of space-time. So the Riemann tensor is, of course, r mu nu alpha beta. Now we can contract on the first and third index to form r mu nu mu beta. And of course you can think of contraction on these indices as multiplying this tensor by the identity delta upper alpha lower mu, and that wires together the first and third index. So this is referred to as the Ricci tensor. And it's a type 0,2 tensor. And the symbol usually given for this type 0,2 tensor is just r nu beta. So r nu beta is just shorthand notation for r mu nu mu beta. And of course we can always distinguish between the Ricci tensor and the Riemann tensor because Ricci just has 2 indices, Riemann has 4. Now you might wonder, why are we contracting on the first and third index? Why not, for example, the first and second index? Well, remember, Riemann tensor is antisymmetric in the first 2 indices, so if we contracted on those, we would be multiplying an antisymmetric tensor, or this antisymmetric in these first 2 indices, with a symmetric tensor, namely the identity, and that would just give 0. We could also contract on the first and fourth index, but remember, Riemann is antisymmetric in the last 2 indices, so that would just give us minus what we have by contracting on the first and third index. So really the only independent contraction of the Riemann tensor is there's just one independent contraction, and it can be defined as contraction on the first and third index. So this defines the Ricci tensor. You'll notice this can be written as r nu beta equals g mu, let's say sigma, r sigma nu mu beta. But now Riemann tensor is symmetric under interchange of the first 2 indices with the second 2 indices. So this is g mu sigma times r mu beta sigma nu. And this factor of g mu sigma raises the first index and wires it with the third index. So this is r mu beta mu nu. But of course, by definition, this is just the Ricci tensor r beta nu. So what you see I've proved here is that the Ricci tensor is actually symmetric. It's a symmetric tensor. From the Ricci tensor, we can form a scalar quantity by contracting on its 2 indices. So we can form g mu nu r mu nu. So the g mu nu raises one index and wires it with the other. And this is type 0, 0 tensor. It's a scalar. So this is sometimes called the curvature scalar. or the Ricci scalar. The symbol we give this scalar is R, and we can distinguish it from the Ricci tensor or the Riemann tensor by the fact that it has no indices. We have one more definition to make, and that's the Einstein tensor. So it's denoted with a capital letter G. So G mu nu, it's a type 02 tensor, is just the Ricci tensor minus 1/2 the curvature scalar times G mu nu. So this is the definition of the Einstein tensor. As you can guess from the name, this is going to play a very important role in our further development of general relativity. And notice also the Einstein tensor is symmetric. It's symmetric because the Ricci tensor is symmetric and because the metric itself is symmetric. One hint as to why this combination of Ricci and the curvature scalar is important can be seen by examining the Bianchi identity. So let's write that down once again. This is del sigma r mu nu alpha beta, and we cyclically permute the first three indices. So this is del mu r nu sigma alpha beta plus del nu r sigma mu alpha beta equals 0. And now let's take this expression and let's contract on mu and alpha. So in other words, let's multiply everything by g mu alpha. Right? And remember, the metric as well as the inverse metric can pass right through the covariant derivative. So this is del sigma. Now this g mu alpha contracts the first and third index, so that just gives the Ricci tensor r nu beta. Here g mu alpha acting on del mu, let's just raise that index and call it del upper alpha r nu sigma alpha beta. And finally, for this last term, we're contracting on the first and second index, mu and alpha. Now remember, Ricci is antisymmetric under interchange of the first two indices, so we could write this as r mu minus r mu sigma alpha beta, and now the g mu alpha just wires together the first and third index to give the Ricci tensor. So this is minus, so I'll make this a minus sign, del nu r sigma beta, and all of that is equal to 0. Now let's contract again on nu and beta, so we'll multiply all of this by g nu beta. All right, passing the g inside the covariant derivative, that just converts this Ricci tensor into a curvature scalar, r. This term is contracting on nu and beta. Well, we can reverse these two indices, call this nu sigma beta alpha, and then we will of course have a minus sign, and then contraction on the first and third index, which gives us the Ricci tensor r sigma alpha. And this last term, we're contracting on nu and beta, so that just wires together. Let me just raise this index nu and call it beta, r sigma beta equals 0. Now simplifying this, we have del sigma r. These two terms are of course the same, so that's minus 2, and why don't I move this index down and this index up? This is del alpha r alpha sigma, and of course it doesn't matter which order I write the indices on the Ricci tensor because it's symmetric. This is equal to 0. And now multiplying through by minus 1/2, we see we can write this as del alpha acting on r alpha sigma minus 1/2 r curvature scalar delta alpha sigma equals 0. But of course this is just the Einstein tensor, big G alpha sigma. So what we've shown is that the Einstein tensor satisfies del mu g mu nu equals 0. And this is sometimes called the contracted Bianchi identity. Because we had to contract the Bianchi identity to obtain it. In fact, we had to contract it twice. So sometimes this is referred to as the twice contracted Bianchi identity. Bianchi identity. Now that we understand mathematically how the curvature of a spacetime is defined, let's take a look at some specific examples. Let's begin with flat spacetime. So we first start with the metric, and from there we can compute the Christoffel symbols. And from the Christoffel symbols we can compute the Riemann tensor. And from the Riemann tensor we can form the Ricci tensor, the curvature scalar, and the Einstein tensor. Now these calculations are particularly easy if we choose Minkowski coordinates. In Minkowski coordinates, this is just eta mu nu, just ones and minus ones along the diagonal. And since the Christoffel symbols always involve derivatives of the metric, this is just 0 in Minkowski coordinates. So all of these quantities are just 0. And of course, since these are tensor relations, we can conclude that they hold in any coordinate system. And in fact, this would be the definition of flat spacetime. Flat spacetime is a spacetime in which the Riemann tensor vanishes. And now for a less trivial example, let's look at the spacetime outside a body that's isolated, spherical, non-rotating, with mass m and electric charge q. So this is a generalization of the Schwarzschild spacetime to a body that not only has mass but also has electric charge q. This is sometimes called the Reissner-Nordstrom spacetime. Right, and the line element for the Reissner-Nordstrom spacetime is minus 1 minus 2m over r plus q squared over r squared dt squared plus 1 divided by this same factor, 1 minus 2m over r plus q squared over r squared dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. So this looks just like the Schwarzschild metric, but with these extra terms, q squared over r squared in the gtt and grr components of the metric. From here we can compute the Christoffel symbols and the Riemann tensor. It's a lot of work, so I suggest you use a computer algebra system to do the calculations. What we find is that, let me just quote some of the results. For example, the TR component of the Riemann tensor is 2mr minus 3q squared divided by r squared times r squared minus 2mr plus q squared. The r theta component, as another example, is q squared minus mr divided by r squared, and so forth. Okay, we can also compute the Ricci tensor. So for Ricci we have the components, for example, RTT is q to the fourth plus q squared times r squared minus 2mr, all divided by r to the 6th power, etc. And the curvature scalar, r, in this example just happens to be 0. So since r is 0, the Einstein tensor then is just equal to the Ricci tensor. So for example, the TT component of the Einstein tensor is q to the 4th plus q squared r squared minus 2mr divided by r to the 6th. And from these calculations we can verify the Bianchi identities. For example, the contracted Bianchi identity, we can verify that that holds. One thing you should keep in mind in these calculations is that the components of the Riemann tensor, like the components of any tensor, depend on the coordinate system that you use. So these results by themselves don't really have any direct physical meaning, because we could change the components by simply changing the coordinates that we're using. But scalar quantities, of course, are different. For example, in any coordinate system, r is going to be 0 if it's 0 in one coordinate system. And scalar quantities always have the same value at any point in the space-time, no matter what coordinate system you use. So it's useful to form scalar combinations of the Riemann tensor, and there are other scalar combinations besides the curvature scalar. For example, the Kretschmann scalar is the square of the Riemann tensor, so r mu nu alpha beta, r mu nu alpha beta. And in this example of Reissner-Nordstrom spacetime, it's equal to 8 times 7q to the 4th minus 12mq squared r plus 6m r squared, that's m squared r squared, all divided by r to the 8th. And another example is the square of the Ricci tensor. So that's r mu nu, and in this example of Reissner-Nordstrom, it's 4q to the 4th power over r to the 8th. So these are quantities that will have the same value in any coordinate system. Now, of course, r, this is the areal radius. R might not be one of the coordinates in your coordinate system, so the result may be expressed differently. It may be that the areal radius has to be expressed in terms of whatever coordinates you're using, but the value of these scalars at any given point in the space-time with areal radius r will be the same no matter what coordinate system you use.